Hello everyone, and welcome to our online course, Software-Defined Networking Helps Enterprises Go Digital. Most of you are probably familiar with new internet technologies, such as cloud computing, big data, the IoT, and CDN, but you might not have heard much about Software-Defined Networking, SDN. So what exactly is SDN? What value does it bring to the internet? With this course, we hope that we can demystify the subject for you. Before explaining the innovative SDN architecture, let's take a look at a typical example of a traditional network architecture. The Internet was created at DARPA, an agency of the U.S. Department of Defense in the 1960s. At the time, the American military wanted a network that could restore itself to operation in the event of a nuclear attack. Centralized control and central nodes were therefore out of the question, as a single bomb could take out the entire network. This requirement on high network availability resulted in networks being deployed in a distributed manner. These distributed networks are what we now call traditional networks. On a traditional network, you'll find common devices, like switches and routers, produced by any number of manufacturers. What you might not know is that all of these network devices have three planes: a management plane, a control plane, and a data plane. When you configure a network device, you're working on the management plane of that device. After you finish the configuration, different protocol computations on the control plane of the device generate all kinds of table entries. Some of the more well-known tables are the MAC table that guides the forwarding of layer 2 frames, the routing table for layer 3 packets, and the label table for MPLS packets. Finally, once a user service packets have reached the device, the data plane of the device is responsible for forwarding them. Now you've got a bit of background knowledge as to how these concepts apply to traditional networks. Traditional networks run in a distributed manner, with each router having its own control plane, the brain of a network device. When a router receives a packet, this brain decides on its own how to forward it. IP networks have used distributed control throughout the past few decades, and this method of control has been extremely successful in satisfying user requirements. However, with the massive growth of traffic and diversification of services occurring at present, fully distributed architectures have led to a number of problems: overly congested networks, complex devices, difficult O&M, and slow deployment of new services. With the advent of LTE and 5G, network bandwidth requirements are rising sharply. This has become a direct cause of network congestion. What methods do we have to alleviate network congestion? Most people would suggest increasing link bandwidth, setting up QoS mechanisms, or deploying TE, but these are unable to alleviate network congestion in real time. Let's look at two examples that illustrate the limitations of traditional networks when it comes to dealing with congestion. First, consider a network running the OSPF routing protocol. We can see that there are three paths from router A to router B, A to B, A to C to B, and A to C to D to E to B. OSPF is a clever protocol. It computes the shortest path from a source to a destination. So in this example, OSPF would determine that the path directly from A to B has the lowest length overhead and is the shortest, and would therefore forward all service packets from A destined for B along that one path. But what if congestion on the link from A to B is already causing packet loss while the other two links are idle? Why not forward some traffic along those links? This example shows us that traditional networks can be both smart and dumb. Smart in that all protocols that they use generate optimal paths, and dumb in that they do not take a global perspective. When congestion occurs on the optimal route, they cannot switch traffic over to other routes automatically. You might be thinking the MPLS TE can resolve traffic scheduling issues, but MPLS TE has to be designed and configured in advance. It can't adjust network traffic to resolve bandwidth congestion issues in real time. Now, let's look at the next example. 3 tunnels have been set up on the MPLS-TE network. The first tunnel runs from A to E, with a planned path of A to B to C to D to E, and has a reserved bandwidth of 6 gigabytes per second. The second tunnel is set up from C to G, with a planned path of C to B to A to F to G. It has a reserved bandwidth of 4 gigabytes per second. And the third tunnel goes from C to D, having a reserved bandwidth of 8 gigabytes per second. You've probably noticed that the total bandwidth on all paths from C to D is insufficient, and MPLS-TE tunnel establishment is going to fail. We can see from this example that if you want to use MPLS-TE or traffic scheduling, you have to design and configure it beforehand. In this case, to successfully deploy these tunnels, you'd have to set the first tunnel to go from A to F to G to H to E, the second from C to G, and the third from C to D. This is what we mean when we say that the traditional networks are not intelligent and cannot resolve network congestion issues in real time. Also, you've probably noticed that the routers on existing networks are quite complex, running a lot of protocols like OSPF, BGP, MPLS, IPv6, and IPsec, all at the same time. The reason for this is that networks are distributed. That means that every device needs to have control plane protocols running on it. By now, the IETF has already defined thousands of RFCs, and that number continues to grow. If you want to become an IP guru, you'll probably have to read more than 2,500 RFCs about network devices. That would take 6 years if you read one a day. And that only accounts for a third of all RFCs, the number of which continues to grow. And if you want to have expert knowledge of a vendor's devices, you'll need to master more than 10,000 commands, a number that's constantly growing, while also taking into account the differences between different vendors. Huawei, Cisco, and Juniper all have different GUIs and different formats for their commands. For a network engineer tasked with maintaining an existing network, learning about and operating the devices of different vendors makes for an incredibly complex job. Now let's see just how difficult it is to perform O&M on a traditional network. Consider a carrier deploying a VPN for an enterprise. To set up PEs on the network, IGPs, BGP, MPLS, and VPN v4 need to be configured. Different interfaces have to be bound to different VRFs, and so on. All in all, that will amount to 50 or more configuration commands per PE. Because traditional networks use a distributed architecture, each PE has to be configured individually. Furthermore, whenever a new PE is added to the network, all PEs involved need to be modified. This makes O&M extremely difficult. The multitude of protocols and commands on IP networks actually isn't the biggest pain point for enterprises. That position is held by the extreme slowness of service deployment. Let's take a look at how a CT company deploys a new service. First, a list of requirements is proposed. To satisfy these requirements, we need a new protocol, and to create a new protocol, we need to define a new standard. The process of protocol standardization usually takes at least 2 years. Then, to support the new protocol, each vendor needs to update its devices and perform interoperability testing. That process takes another year. Afterward, updates need to be deployed at scale on existing networks. Smaller changes may only require software upgrading, but larger changes can require hardware replacement, which is very tedious. All things considered, it will take 3 to 5 years before the service deployment is complete, much too slow for OTT providers, which often require network modifications to be performed quickly. To the contrary, IT companies' applications can often be tested, deployed, and delivered only a short time after requirements are proposed, and service features can be updated every month, week, or even day. And why is it that IT companies are able to deploy services so much faster than CT companies are? The reason is that they are based on software. On a traditional network, the deployments of an innovative network service must pass through all these steps precisely because network control is distributed. Basic layer 2 and 3 devices in particular must interoperate with many other devices. The interoperability must be standardized, and the standardization process also requires interoperability testing. For these reasons, upgrading the control plane on traditional distributed networks commonly require large-scale network-wide upgrades as well.